Okay, so the last section of this chapter, section 3.7, asks us to combine what we've learnt about hypothesis testing from previous chapters and from last year with the normal distribution. Now, the specific way that you use a hypothesis test with the normal distribution is that if you have a population or a set of data that is normally distributed and you want to find out, you want to take a sample from this data. And you want to find out whether or not this is a good representative sample, whether or not this sample represents the population well. Basically, what you want to do is test the sample and see whether the mean of the sample is statistically significant. Now, what happens is in normally distributed data that if you take lots of random samples, then the means of each of those samples form a normal distribution themselves. So by that, what I mean is you have a normally distributed population. You take a sample of whatever size from it. Let's say we take a sample of size 50, and you find the mean of this sample, and then you take another sample of size 50 and find its mean, and then you take another sample of size 50 and you find its mean, and you just keep going and keep going. Now, depending on how big the population is, you might be able, in theory, if you had a huge amount of time, to take all possible samples of size 50. Now, if you did, you would find that the actual mean of the population occurred the most frequently, and the next most frequent means would be quite close to the mean of the actual population, and so on and so forth. So each of these samples has a mean, and if you see how often these means occur, then these means themselves form a normal distribution. So if you've taken all possible samples, you know that the most commonly occurring mean is going to be the same as the mean of the original population. So we can do hypothesis testing on a sample to test about whether or not the sample resembles the population mean. We call our sample X, and we call the mean of a sample capital X bar, and you've seen this X bar notation for mean before. So if we have a random variable X, which is normally distributed with mean and variance like we're used to, then if you take a sample, then the sample mean, X bar, is also normally distributed with a mean mu, but a variance sigma squared over n, where n is the sample size. So what we want to do is take a sample and test whether or not the mean from this sample, we'll call this mean from this individual sample, lowercase x bar, whether or not that's statistically significant. So the easiest way to explain this is just to look at examples and look at it in action. We have, in example 14, a certain company sells fruit juice in cartons, and the amount of juice in a carton has a normal distribution with a standard deviation of 3 mils. So if we let X be the amount of juice in a carton, we're dealing with this. A normal distribution, mean, we haven't been told that yet, but a standard deviation of 3. So we've got 9 or 3 squared for the variance there. Now, the company claims that the amount of juice per carton is 60 mils. So the claim is this. However, it says that a trading inspector has received some complaints that the company is overstating the mean. So they're saying the mean is too much. He wants to investigate the complaint. So what he does is he takes a random sample of 16 cartons. Let's make a note of this to the side. And he finds that in this sample, the mean amount of juice is 59.1, which is of course less than 60. So he thinks that the mean is actually less than that, and the company is overstating the truth here. So we are asked to use a 5% level of significance and test whether or not there is evidence to uphold the complaint. Is it really the case that, or do we have enough evidence to say that the mean is actually less than the company claims? So here we go. We're going to state it all properly. I've written this first of all just to kind of help you, but let's state it very clearly now. So we are saying that we're going to let X be the amount of juice in a carton. X is normally distributed with a mean of 60 and a variance of 3 squared. And null hypothesis is that the mean is 60. So remember, that is, stick with your initial assumption. The alternative hypothesis is actually it's less than that, and that's what we want to find out. And we have a sample taken, and we're going to assume that's normally distributed, so mean 60, but the variance of the sample is the variance of the original divided by the sample size. So we've got 3 squared over 16 for the variance here. Now, let's have a look. Just making sure I can read the next bit so I don't miss out any information. If I now work out 3 squared over 16, 9 over 16. So the variance of the sample is that, but the standard deviation of the sample is 0.75 or 3/4. So let's make a note of that. So the sample variance is 9/16 and the sample standard deviation is therefore 3/4. I always like to make a note of these explicitly to try and help me use the right numbers in the right places so that I don't accidentally write something down wrong, because we're all prone to making mistakes like that. So let's have a look at what's going on here. If we sketch this normal distribution, this is x bar here, with a mean at 60. That's our assumption anyway. But however, the inspector finds his mean to be 59.1. So I want to know, what's the chances of that happening? What's the chances of us being 59.1 or less? Because we're seeing whether or not the mean is actually less than 59.1. So let's use our calculator to work out that probability, shall we? We go to normal cumulative, take a really lower bound here, and the upper value is 59.1. Sigma was 3/4. And our mu, we're assuming it's 60. And that gives us a probability here of 0.1151. That's a 11.51% chance. Now let's make sure you're really clear with what's happening here. What we're saying is, if our assumption is correct, if the mean is actually 60, then we have an 11.51% chance of taking a sample with a mean of 59.1. That's a pretty decent chance. Now, how decent is it? Well, we are testing this at a 5% level of significance. So what we need to do is compare this chance here to our 5% statistically significant cutoff point. So we say, therefore, let's write it down explicitly, the probability that the sample mean is less than 59.1 is 0.1151. That's 11.51%. So we say 11.51%, that's greater than 5%. So it's a pretty decent chance of it happening. So we haven't got enough evidence to reject our initial assumption. If this was small here, less than 5%, we would say, that's quite unlikely actually. I think our assumption was wrong. But it's not that small. It's much bigger than our 5% cutoff. So we don't have enough evidence to reject this. So we now need to say 2 things. We say there is insufficient evidence to reject H0, our null hypothesis, but now we must write a sentence in the context of the question. So the context of the question was, can we uphold this complaint? So we say there is no evidence, or not no evidence, but we can say there is not enough evidence to uphold the complaint. Now, as with all hypothesis testing, it depends on your cutoff level. If you wanted to test it at a 10% level, then you're pretty close, but you would still stick with your null hypothesis, even at a 10% level of significance. 5% level of significance is pretty decent, because if a chance of something happening is less than 5%, you can quite confidently say that's an unlikely thing. You can still end up rejecting a null hypothesis incorrectly, because it can still happen. 5% chance of something happening is still a 5% chance that it can happen, but we just have to go on the balance of probabilities here. So in this case, there's not enough evidence to uphold the complaint. So the way this can get slightly more in depth is working out the critical regions for a test statistic. So sometimes we want to know what is the value that would cause us to accept or reject a null hypothesis. That value is called a critical value, and any values that fall less than or greater than critical values, depending on if you have a lower tail or an upper tail, are called the critical region. So to find a critical region, what we're going to do first of all, I'm going to show you the method whereby we standardise our test statistic. I'm struggling to say statistic today. Let's try again. To find a critical region, we are going to standardise the test statistic. And don't forget, that is our sample mean, x bar. So I need you to remember something from exercises 3D and E, and that was that to standardise x, you subtract the mean from it and then you divide by the standard deviation. So to standardise our x bar, we're going to subtract the mean, but we are then going to divide by this standard deviation, which is the square root of this variance. So that would be sigma over root n, square root the sigma squared, square root the n. And that gives us a standard normal distribution with a mean of 0 and a variance or a standard deviation of 1. Let's look at this in action so it makes more sense to you. What I need you to do first of all then is have a read of the question. Make sure you've got it in front of you. It's example 15, and it tells us that a machine produces bolts of diameter d, and d has a normal distribution with a mean of 0.580 centimetres and a standard deviation of 0.015 centimetres. So don't forget we write squared here. Now it tells us that the machine gets serviced, and after the service they want to know whether or not these parameters have changed. So what they do is they take a sample of 50 bolts from the next production run, and they find the mean of these 50 bolts to see if it's changed from 0.580. What they find is that the standard deviation of the bolts that they test is still 0.015. So before they actually tell us what the mean is, the question is asking us to find out what's the critical region for this test, what's the values that would cause us to assume that this has actually changed, and they want us to do it at a 1% level of significance. So let's start then by stating what the null and alternative hypotheses are. So the null hypothesis is we assume that the mean has remained the same. The alternative hypothesis, we don't know if it's increased or decreased. What they're asking us is, has it changed? So the alternative is that it's not equal to this. And don't forget, this symbol, not equal to, means you're going to do a two-tailed test. So what we do first is we say that we assume the null hypothesis. So our bolts diameters are normally distributed with this mean and this standard deviation and this variance. But then we assume that for the sample it's the same, except that for our sample the variance gets divided by the sample size. So 0.015 squared divided by 50, because n was 50. Now, we're going to standardise this. So we are going to let Z be the diameter, the mean of this sample of diameters. And we subtract the original mean and we divide by this new standard deviation. So 0.015 over root 50. Remember, it's the standard deviation here, so it's the square root of this value. Now, what we're going to do next is a sketch of what's going on. At this point, we've standardised. So we're going to draw ourselves the standard normal distribution with mean at 0. And it wants us to work out at a 1% significance level, but a two-tailed test. So that's going to be a 0.5% in each tail. So we want to know if this area is 0.5% or 0.005, and this area is 0.5%, so also 0.005. We want to know what is this value and what is this value. So let's go to our calculator and normal cumulative distribution. At the lower end, we're going from, I'm just going to reset this because it automatically defaults to, oh no, it doesn't. I'd have to actually turn it off and on, but we won't bother now. So I'd go from minus 100, I'm doing the wrong one. I want the inverse normal. Try again, inverse normal, because what we know is the area, 0.005. We're dealing with a standard normal distribution, so sigma is 1, mu is 0. And this value is minus 2.5758. Now, for this value, don't forget the inverse normal uses the area to the right, to the left, the less than area. So if that's 0.005, I need to type in here 0.995 because I want all the area all the way down there. And that gives me a value of 2.5758. So what I need to do now is work out the value of d bar, or the mean of d that produces this and that produces this. So I'm going to put this equation, this expression here, equal to each of these values independently. So at the lower end, I have got d bar minus 0.580 over 0.015 over root 50. And notice I've used a lowercase d here because I'm not looking at the whole distribution, I'm looking at an individual value on it, equal to minus 2.5758. So let's solve that one. Minus 2.5758 times by 0.015 over root 50. And then we're going to add 0.580. And that gives me d bar is 0.5745. That's the first one. Now let's do the second one here. So d bar minus 0.580 over 0.015 over root 50 equal to 2.5758. So let's just go back and change this number to 2.5758 and then add 0.580, and that gives me d bar as 0.5855. I've done that one to 4 decimal places, so I'll keep this one to 4 decimal places as well. So the thing here then is we have worked out that on the original distribution, the d bar, the d bar distribution, that the chances of us being less than this mean is 1/2%, and the chances of us being greater than this mean is 1/2%. So I need to write down my critical region. So I'm going to come up here. So the critical region is any mean less than 0.575 or any mean greater than, let's use, I've rounded there, but because that's a 5 and this is a 4, actually if I do this to 3 decimal places it'll be 0.585. 0.585 there. So this is my critical region, and what it means is in this sample of 50, if the mean of the sample is in either of these regions here, then we would say we have got enough evidence to assume that the mean has changed. Now let's have a look at part B, because in part B it actually tells us that the of the sample that they take, the observed mean is 0.587 centimetres. And they want to know, does that mean give us enough evidence to think that the overall mean on the machine generally has changed? Well, this here falls in this upper region because it is actually bigger than 0.585. So we need to say, since 0.587 is greater than 0.585, this falls in the critical region. Now what does that mean? It means we have enough evidence to reject our null hypothesis, H0. Now, once you say whether or not you stick with your null or you reject your null, you then always write a sentence in context. So what does it mean to reject the null hypothesis? Well, that means we're looking at this one and we're saying that the mean has changed. So we can say we assume that the mean diameter has changed. There we go. So you can now have a go at exercise 3G. Good luck. Get in touch with your teacher if you need some help.